We're going to talk about standing waves, resonance, and harmonic. Starting with a recap, I'm going to show you this. I'm going to adjust the tension right here on this musical instrument, and I want you to tell me why the pitch goes up. So we change this, and you'll notice that changes. So why does the pitch go up? So just a quick recap of constants. You know that the velocity of wave on a string equals frequency times lambda. You also know that velocity of a wave on a string is equal to the square root force of tension over the linear mass density. So if we look at this, we know that the frequency is going to change. You get the frequency equals v over lambda. If velocity goes up, then frequency also goes up and we hear a higher pitch noise. So here are the big ideas for this video. I'd like you to write these down because they will be on your test. So we're going to talk about superposition. We've already talked about this. If you have two waves, and this is your original waveform, if your second waveform directly aligns with it, the amplitude gets even bigger. This is constructive interference. And interference is kind of a horrible word, but that's okay. Likewise, if you have a waveform, and then the negative of that waveform, you have nothing plus something, or negative, big negative plus big positive, flat lines here. 0 plus 0, still 0. Plus 1 minus 1, still 0. So when you add wavelengths, when they interfere, you add the amplitudes. Add the amplitudes. So this would be noise-canceling headphones. This would be trying to get a really, really loud noise by all humming the same note. If we look at how these waves interact, this is our base wave. And let's say that they're emitted at different places, but they have the same frequency. Same frequency. They go up and down at the same rate. If we look at this first wave, we see that delta L, this is one full wavelength. This is lambda. Of course, we could also see that if it was two full wavelengths, if this is in lambda, you get constructive interference. I'm going to go ahead and write this as in lambda over 2, where n equals an even number. This is just because if we're examining, when you hit your origin point where this wave starts and this wave starts, this one went up and down, now it's going up, this one's going up, and the peaks match. If, however, you have a part where they're out of phase, maybe this is in lambda over 2, where n equals odd. Say that it only gets 1/2 wavelength, 3/2 wavelength, something like that, you'll see that as this wave's going down, this one's going up, and you get destructive interference. Over 2, this is for n is odd. And based off this, if you have your speakers or whatever is emitting the same frequency noise at different positions, you will find that you get direct constructive interference or direct destructive interference. If it's somewhere in between here, you get a mix match. Another way that you can see interference is by this term beats. So if you look, we have two tuning forks. This tuning fork has an extra mass. What's that mean its frequency is going to be? Higher or lower than this one. So this is a blank frequency than the other. Okay, lower. So let's see what happens when we play them. And their frequencies are just a little bit out. So we hit them. Whoops. See how it gets really loud, really soft? We call those things beats, kind of that wobble. Every time it hits really hard, you get a beat. And that's when your waves are constructively interfering. So if you find your frequency of your beats, this is just the absolute value of f1 minus f2. The difference between your two frequencies gives you your frequency of your beats, the frequency of that wobble that you'll hear. So for another case of superposition, let's say we've got these two fixed surfaces shown in blue, and you send a wave through. A wave hits this wall, it reflects at 180 degrees, and comes back right here. And you can see that if you've got the proper frequency, it will just keep retracing the same path over and over again. It looks like wiggles, except at these points right here. These points don't move at all. We call the points that don't move nodes. There's node, 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 node. And then we call the points that have maximum movement antinodes. So this wave looks like it's just going to go back and forth, 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 back and forth. And it doesn't look like the wave's moving at all. And they call this a standing wave. We're going to get into the math in class, but right now the important part is just to visualize that this wave is going to keep retracing the same path over and over again. And it's also the basis for musical instruments. In the case of strings, you've got your frets fixed right here, so like a violin, a guitar. So you fix nodes at either side. And then you'll see that this total length right here, the length is equal to lambda over 2, which also means that lambda equals 2 times the length of this column. Sorry, the L went off the page. If we rewrite this, you get that the fundamental frequency just means the first harmonic. When you get these standing waves, you get music or notes. So fundamental frequency equals V over 2L. If we look at this second case, right here, second case, that's one full wavelength. So L is equal to lambda, or you get the second harmonic, the second little overtone standing wave that you can introduce in this is equal to V over L. I'm going to go ahead and write this as 2V over 2L. What about the third? Well, we've got L equals 3 lambda over 2, or F3 is equal to 3V over 2L, L being the length of the tube. So if we examine these, we get frequency. The nth harmonic on a string is equal to NV over 2L, where N equals 1, 2, 3, yada, yada, yada. Keeps on going. You can keep playing notes. So let's look at how this happens, or what this actually does. So we're going to start by playing a note. And then we're going to move the fret a little bit. So what does that do to length? Okay, so let's look at air columns now. These would be like your woodwind instruments, or panpipe. For wind instruments, this is a little different. Again, this is showing a transverse wave, but what it actually is, since air is going to go and sound travels in a longitudinal wave, this part where you have zero displacement, that means zero displacement in the air here. This, on this end, you get maximum displacement on the air. So that's why we show it with these waves. So if we look here, this is just this part of the wave, which is a quarter wavelength. So this would be lambda over 4, which means your first harmonic that you're going to introduce in here is V over 4L. Your second, well, this is almost a wave. You're just missing that 1/4 of it. So this is 3 lambda over 4, or 3V over 4L. How many are in this second? Or sorry, third case. Well, third case, well, that looks like 5/4 lambda. So you get 5V over 4L. And you'll notice that we're missing pieces here. It just goes 1, 3, 5. So this, we call this our third harmonic. We call this our fifth harmonic, just so our number stays the same. But you're missing all these other harmonics that overlap. So here, your nth harmonic, the nth note that you can make, is equal to NV over 4L. But the key part of this, with the open air column on one side, closed on the other, your N equals 1, 3, that's a 5, 1, 3, 5. This is a very different result, but it's very important. And on to an air column open on both sides. If you have a wind instrument that's open on both sides, now you can get displacement on both sides. So how many wavelengths is this? Okay, good. That means L is equal to lambda over 2. It's just a half wavelength, or that your first frequency is equal to V over 2L. I'll take a look at the second ones. How many waves are in part 2, and how many waves are in this third part down here? Give you a minute to think about that. By a minute, I mean a couple seconds. Hit pause. You can actually let it be a minute. So if we look at this, this is exactly like waves on a string. If you'll notice, this actually skipped a case. In fact, this is actually the fourth one. And you can get that this is the fourth one by counting the number of nodes. 1, 2, 3, 4. This tells you that this is the fourth harmonic. I skipped some just to make sure you were still on your toes. So getting the formula for this, we get the nth harmonic for waves on an open air column. Open means open on both ends, is just NV over 2L. And then in this case, there are no exceptions, so N is 1, 2, 3, and keeps on going. Right. So these represent fundamental frequencies. These are frequencies that instruments vibrate. And if you can vibrate something at the natural frequency, you will show what is called a resonance. We're going to show a couple examples of this in class. It's one of my favorite demos to show. They're all my favorite. I love physics, what we're talking about. So anyway, what you've covered, you have learned about waves on a string, vibrations, fundamental frequencies, and then harmonics, which are just multiples of those fundamental vibrations. I hope this helps, and I will see you in class.